So this is section 8.4, which is about matrix algebra. Basically performing operations on matrices, adding them, subtracting them, multiplying them, etc., etc. Now, usually speaking, when we talk about a matrix, we denote it with a capital letter like A, B, or C, and that's just how we do it. We use lowercase letters to talk about elements that are inside the matrix. So we can say matrix A, which is capital A, is equal to a matrix that has elements little a sub ij. Now, in this lowercase here, you see this little subscript ij. The ij refers to the location in the matrix of each element. So the first number I tells you what row an element is in, and the second number j tells you what column it's in. So for example, if you saw A sub 3, 2, that tells me that you're looking at the element that is in the third row and the second column, not fifth, second column. Okay. Now, when we talk about matrices, they do have rows and columns, which gives them what is called an order. An order basically says how many rows and columns they have. So an M by N matrix is a matrix that has M rows and N columns. Rows always comes first, columns always come second. Now, if these two numbers happen to be the same, you have MM or NN, then that matrix is called a square matrix. And it would be a matrix that has the same number of rows as it does columns. So let's just take some of this and apply it in an example here. So example 1 says, let matrix A be this matrix 3, 2, 0, negative 4, negative 5, negative 1/5. The first question asks us, what is the order of matrix A? So what is its size? Well, it has 2 rows and 3 columns, so it would be a 2 by 3 matrix. The next part says, if this matrix has these elements A sub ij, identify A sub 2, 3 and A sub 1, 2. So A sub 2, 3 means we're going to the second row and third column. So second row, third column is negative 1/5. A sub 1, 2 means I go to the first row, second column. So first row, second column is 2. Okay. So it's pretty easy to say the order, the size of the matrix, and find elements in it. Now, two matrices are considered equal if and only if they have the same order, meaning they're the same size, and corresponding elements are equal, meaning that the element that's in row 1, column 1 of the first matrix is also the same thing in row 1, column 2, or row 1, column 1 of the second matrix. So corresponding elements have to be the same. So that's the only way two matrices can be equal, same size, same order, and corresponding elements equal. Now let's actually get into some operations. If two matrices have the same order, the same size, then you can add or subtract them. To do that, you just add or subtract corresponding elements, meaning the element that's in row 1, column 1 of the first matrix, you add that to the element that's in row 1, column 1 of the second matrix, or subtract. Okay. Now, if matrices have different sizes, different orders, you cannot add it and subtract them. It's just not possible to do the operation. Okay. So let's look at an example of this. We have a matrix 0, 5, 3, negative 2, 6, negative 8, and another one, negative 2, 3, 5, 7, negative 9, 6, and we want to add them. Well, this matrix has 2 rows and 3 columns. This one has 2 rows and 3 columns. So they are the same size, so I can add them together. So when I add them together, I'm going to take the first element here and add it to the first element here. So 0 plus negative 2 gives me negative 2. The next one, 5 plus 3, 8. Next one, 3 plus 5, also 8. On the bottom row, negative 2 plus 7 is 5. 6 plus negative 9 is negative 3. Negative 8 plus 6 gives me negative 2. So there's what I get when I add those two matrices together. All right, for B, we have a matrix negative 6, 7, 2, negative 3, minus another matrix negative 5, 6, 0, negative 4. This matrix is a 2 by 2. This matrix is also a 2 by 2. Since they have the same size, the same order, we can subtract them. So I'll start with the first element. I have negative 6 minus a negative 5. And just so you can see this, negative 6 minus a negative 5. Since it's minus a negative, it's really a plus. So negative 6 plus 5 gives me negative 1. For my next element, I have 7 minus 6. 7 minus 6 is 1. On the bottom row, 2 minus 0 is 2. And then the last element, we have negative 3 minus a negative 4. And again, just so you can see this is negative 3 minus a negative 4. Since it's minus a negative, that means it's really plus. So negative 3 plus 4 gives you 1. And so that would be our result from that subtraction. So addition and subtraction are not too bad to do with matrices, just add like elements or subtract like elements. So we're going to go into a little bit more terminology. A matrix whose elements are all 0 is called a zero matrix. And if you take a matrix A that is m rows and n columns, m by n, and you add to it the 0 matrix, which is m by n with all zeros in it, then that matrix A plus the 0 matrix still gives you matrix A. Now, this 0 matrix is called the additive identity. Because basically it says that when you take this matrix and you add the 0, 1 to it, you do not change it. So you're getting the same thing. It's an identity. Okay. Now, the additive inverse, which we usually write as a negative A or an inverse A, this is a matrix where when you add it to the original matrix, you get the 0 matrix. So like here's an example. I have 5, negative 2, negative 3, 7. I'm adding it to this matrix, negative 5, 2, 3, negative 7, and it gets me the 0 matrix. So in context, this would be A, and this would be the additive inverse. And so when we take these two things and we add them together, we get the 0 matrix. So that's just a little bit of terminology for you. You can see here some properties of matrix addition. There is a commutative property. Matrix A plus matrix B is the same thing as matrix B plus matrix A. The order in which you add them does not matter. There's also an associative property. A plus B, then plus C is the same thing as B plus C and then plus A. It doesn't really matter which order you add them in, it's okay. Additive identity we just talked about. When you take matrix A and you add 0, you get A. Or if you take 0 and you add the A matrix, you still get A. And then additive inverse we just talked about. When you take A plus the additive inverse, you get 0. Or if you take the additive inverse and add A, you also get 0. Now, one thing to keep in mind is there is a difference between a matrix and a number. You can have a matrix that is a 1 by 1, like this matrix here. It is a 1 by 1 that contains just the element 6. This is not the number 6 by itself, though. This is a matrix still. It's just a matrix that happens to contain the number 6. When we have just a number by itself, we don't call it just a number by itself. We actually have a name for it. We call it a scalar. So a scalar is a number that's not a matrix, it's just a number by itself. Now, it's actually really easy to take a scalar number and multiply it to a matrix. So in order to do that, you basically just take each element of the matrix and you multiply it by the scalar. So here you can see if we have a matrix A, which has elements A sub ij, when we multiply that matrix A by a scalar called C, that C just goes to every element in the matrix. So you have C times A sub ij. So each element of the matrix gets multiplied by the scalar number. So let's look at how that works. So in example 3 here, it says if matrix A is negative 1, 4, 3, 0, and matrix B is 2, negative 3, 5, negative 6, find the following matrices. We have, first off, negative 5B, which means I have negative 5 times this B matrix, 2, negative 3, 5, negative 6. This negative 5 is a scalar, so it multiplies to everything in the matrix. So negative 5 times 2 is negative 10. Negative 5 times negative 3 is positive 15. Negative 5 times positive 5 is negative 25. And negative 5 times negative 6 gives us positive 30. And so that would be the result of that scalar multiplication. Now we can also combine scalar multiplication with addition or subtraction. So you can see that here in part B. We have 2A plus 3B. That means I have 2 times this A matrix, negative 1, 4, 3, 0, plus 3 times this B matrix, 2, negative 3, 5, negative 6. You would start by doing the scalar multiplication. So for this first one, we multiply the 2 in. So 2 times negative 1 is negative 2. 2 times 4 is 8. 2 times 3 is 6. 2 times 0 is 0. Over here on the second one, we're going to multiply the 3 scalar in. So 3 times 2 is 6. 3 times negative 3 is negative 9. 3 times 5 is 15. And 3 times negative 6 is negative 18. Once we get done with the scalar multiplication, then we can add these two matrices together. So negative 2 plus 6 is 4. 8 plus negative 9 is negative 1. 6 plus 15 is 21. And 0 plus negative 18 is negative 18. And so there would be the result of doing the two scalar multiplications and the addition. All right. Underneath example 3 here, you can see some properties of scalar multiplication. So if you have two scalars getting multiplied and then that gets multiplied by A, it's the same thing as multiplying A by one of the scalars and then multiplying by the other scalar. So which order you do it in doesn't matter. You can either do the two scalars together and then do the matrix, or you can do one scalar in a matrix and then do the other scalar. The next property is the scalar identity property. If you multiply a matrix by the scalar 1, you just get that same matrix you started with. Distributive property, if you have a scalar C times A plus B, that C can be distributed in and you get C times A plus C times B. Similarly, if you have C plus D getting multiplied by matrix A, the matrix A can be distributed in and you get C times A plus D times A. So there's different properties we can use when we are manipulating scalars. Now we can actually take this stuff to help us solve some simple matrix equations. So if we look here at example 4, it asks us to solve for x in the matrix equation 2x plus a equals b. So I'm just going to rewrite that over here, 2x plus a equals b. So we're going to do a little bit of algebra to solve this thing for x. We'll start by moving the a over, so we'll have 2x equals b minus a. Then to get rid of the 2, we would have to divide, but what's another way of saying divide by 2? Well, we could multiply by a half. So we could take this whole thing, multiply everything by a half. So 2x times 1/2 would just give you x. 1/2 times b is 1/2 b, minus 1/2 times a is 1/2 a. Now, we could leave it like that, or if we wanted to, we could factor the 1/2 out, and we could have just 1/2 times b minus a, and that would work too. So we know x is going to be 1/2 times whatever b minus a is. So let's figure out what that would be in the context of this problem. So start by finding b minus a. Matrix B is -6, 5, 9, 1, minus matrix A is 1, -5, 0, 2. Subtract them. -6 minus 1 is -7. 5 minus -5, just so you can see, 5 minus a -5, that really means 5 plus 5, which gives us 10. 9 minus 0 is 9, and 1 minus 2 is a -1. Oops, should be just 9, not -9 there. Okay, so that's what b minus a gives us. We still need to do 1/2 times that, so we're going to do 1/2 times b minus a. So that means we have 1/2 times this matrix we just found. -7, 10, 9, -1. Distribute the scalar of 1/2 into the matrix. You get -7/2, 5, 9/2, and -1/2. And so that's what matrix X would equal, that matrix right there. Okay, so you do a little bit of algebra to solve for what you're looking for, and then you just do a little bit of matrix math to get your answer. So it's not too bad. All right, now, for matrix multiplication, it's a little bit harder. Matrix multiplication is not as easy as matrix addition or matrix subtraction. In multiplication, we don't multiply corresponding elements. Instead, we do what is called row by column multiplication, meaning we take the row of the first matrix and we multiply it by the column of the second matrix. So, for example, if I have two matrices A and B, where matrix A is A, B, C, D, and matrix B is E, F, G, H, when I multiply together, to find this first element in row 1, column 1, I'm going to take row 1 of matrix A, which in this case is AB, and I'm going to multiply it by column 1 here, which is EG. So I'm going to take A and multiply it by E. I'm going to take B and multiply it by G. And so I'll have AE plus BG. Over here, when I get to the next element, this is row 1, column 2. So I'm going to take row 1 of matrix A, which is AB, and multiply it by column 2 of matrix B, which is FH. So A times F, B times H, we get AF plus BH. Down here, this element is row 2, column 1. So I'm going to take row 2, which is CD, multiply it by column 1, which is EG. So I'll have C times E and D times G. So I'll get CE plus DG. And then for this last element, this is row 2, column 2. So I'm going to take row 2, which is CD, multiply it by column 2, which is FH. So C times F, D times H. I get CF plus DH. So that's kind of the way our process works. We take a row and we multiply it by a column. And then we go into the next one. Row by column, row by column. Okay. And this just kind of shows you how it works more what I just explained. So you take the first row of A, the first column of B, multiply them together, add the products. There you go. That's what goes in that spot there. And then you repeat for the next spot, and the next spot, and the next spot. Okay? So, let's look at an example of this. Example 5 asks us to find A times B, given that matrix A is 2, 3, 4, 7, and matrix B is 0, 1, 5, 6. So AB is going to equal, so for this, well, first off, I'm just going to draw some blanks so you can kind of see where we're working. Okay, so we're going to end up with a 2 by 2 here. So in this blank right here, I'm going to be taking, well, first off, this blank is in row 1 and column 1. So it's row 1, column 1. So I'm going to be taking row 1 of this matrix, which is 2, 3, and multiplying it by column 1 of this matrix, which is 0, 5. So I'll take 2 and multiply it by 0, plus 3 and multiply it by 5. So 2 times 0, 3 times 5. For the next element over here, I'm going to be taking, this is still row 1, but now it's column 2. So I'm going to take row 1, which is 2, 3, and I'm going to multiply it by column 2, which is 1, 6. So I'll have 2 times 1 plus 3 times 6. Okay. Going down to this element, this is now row 2, column 1. So I'm going to take row 2, which is 4, 7, multiply it by column 1, which is 0, 5. So I'll have 4 times 0 plus 7 times 5. For this last one, this is row 2, column 2. So I'm going to be taking row 2, which is 4, 7, multiplying it by column 2, which is 1, 6. So I'll have 4 times 1 plus 7 times 6. And then we clean those numbers up. 2 times 0 is 0. 3 times 5 is 15. 0 plus 15 is 15. 2 times 1 is 2. 3 times 6 is 18. So you have 18 plus 2. That gives us 20. Down here, 4 times 0 is 0. 7 times 5 is 35. So 0 plus 35 is 35. And then down here, 4 times 1 is 4. 7 times 6 is 42. So 42 plus 4 gives us 46. And so there is our matrix product. Now you can check these with your calculator. It does take a lot of typing though. So to do this, I actually have to put both of these matrices in my calculator. So I have to go into my matrix menu. I have to go edit matrix A, make it a 2 by 2, and put in those numbers 2, 3, 4, 7, and then quit, and then go back to matrices, go over to edit and edit matrix B, and make it a 2 by 2, and put in the numbers 0, 1, 5, 6. Oops. 5, 6. And then once we have both of those in there, I can pull up my matrix menu, say take matrix A, and take matrix B, multiply them together. There we go, 15, 20, 35, 46, which is exactly what I have right here. So you can do it in the calculator, but it does involve quite a few keystrokes. You have to sit there and actually input each matrix and then tell it to multiply them together. Now, the little formula that was up here in this box, AE plus BG, AF plus BH, CE plus DG, CF plus DH, that only works if you're multiplying a 2 by 2 times a 2 by 2. What if you're not multiplying those, though? What if it's different sizes? What if it's a 2 by 2 and a 3 by 2 that you want to multiply? Or what if it's a 4 by 1 and a 3 by 4 that you want to multiply? How do you do it? Well, there's actually something you have to check first. Sometimes you can do matrix multiplication and sometimes you cannot. So in order to tell whether you can or cannot, you have to look at the orders and do a little bit of a comparison. So let's say that matrix A is m by n and matrix B is n by p. If these inner numbers here are equal, in this case n is equal to n, if these two numbers are equal, then you can do the multiplication. When you do the multiplication, the size of your answer comes from the outer numbers. So your answer is going to be m by p. Okay? So the inner numbers need to be the same so that you can do the multiplication, and the outer numbers tell you the size of your result. Okay. Now, if the inner numbers are not the same, then you cannot do the multiplication. That multiplication does not exist. Now, if your multiplication does exist, then what you should do is set up a matrix that has the size of the answer, and then do the same kind of thing we just did. Take your rows and multiply by your columns. Row 1 times column 1. Row 1 times column 2. Row 1 times column 3, for however many columns you have. And then row 2 times column 1. Row 2 times column 2. Row 2 times column 3, for however many columns you have. Just keep doing that until you filled in your matrix. Okay. Let's look at some examples here. So example 6 says matrices A and B are defined as follows. Matrix A is 1, 2, 3, and matrix B is 4, 5, 6. And they ask us to find the products, AB and BA. Okay. So for AB, we need to first check the sizes of A and B. A has 1 row and 3 columns. B has 3 rows and 1 column. So check these numbers, see are they equal? Yeah, they're the same, so yeah. So that tells us our answer is going to have these numbers as its size, so our answer is going to be a 1 by 1. So when we do our matrix AB, we expect to take this row, 1, 2, 3, multiply it by this column, 4, 5, 6, and we expect to just get a 1 by 1. So I'm just expecting to get 1 element in there. Well, to find that 1 element, I'm going to take this row and multiply by this column. So I'm going to end up with 1 times 4 plus 2 times 5 plus 3 times 6. So what is that? 4 plus 10 plus 18, so 32. So there would be my 1 by 1 answer. Then they ask us to find BA. Well, for BA, we have to do our check again. So matrix B is a 3 by 1, 3 rows, 1 column. Matrix A is a 1 by 3. So if we check these, are these inner numbers the same? Yeah, they are the same. So since they're the same, we can tell that our answer will have these outer numbers as its size, so it will be a 3 by 3. So when we set it up, we're going to have B times A, which is the matrix 4, 5, 6, times the matrix 1, 2, 3. And we expect our answer to be a 3 by 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3. So to find the element here in the first row, first column, we are going to take the first row of this, which is 4, multiply it by the first column of this, which is 1. So we'll have 4 times 1. For the next one, this is the first row, second column. So I'm going to take the first row of this, which is 4, multiply it by the second column of this, which is 2. So I'll have 4 times 2. For this element, this is first row, third column. So I'm going to take the first row, which is 4, multiply it by the third column, which is 3. So I'll have 4 times 3. Next one, this is second row, first column. So I'm going to take the second row, which is 5, multiply it by the first column, which is 1. So I'll have 5 times 1. For this element, this is second row, second column. So I'm going to take the second row, which is 5, multiply it by the second column, which is 2. So I'll have 5 times 2. For this element, this is second row, third column. So I'm going to take my second row, which is 5, multiply it by my third column, which is 3. I'll have 5 times 3. This next one, this is row 3, column 1. So I'm going to take row 3, which is 6, multiply it by column 1, which is 1. So this is 6 times 1. The next element, this is row 3, column 2. So I'm going to take row 3, which is 6, multiply it by column 2, which is 2. So I'll have 6 times 2. The last element, this is row 3, column 3. So I'm going to take row 3 here, which is 6, multiply it by column 3 here, which is 3. So I'll have 6 times 3. And then we can go in and clean these up. So this is 4, 8, 12, 5, 10, 15, 6, 12, 18. So that's my my 3 by 3 matrix, the 9 elements of it. Again, you can check yourself with a calculator if you want to type this in. So we have to go to our matrix menu and go to edit. We'll edit matrix A so that it becomes a 1 by 3. And we put 1, 2, 3 into it. Quit. Go back to our matrix menu, put matrix B. This is a 3 by 1. Put in it 4, 5, 6. Then quit again. Take matrix A times matrix B. And we get just a matrix with 32. If we take matrix B and we multiply it by matrix A, we get this 3 by 3, 4, 8, 12, 5, 10, 15, 6, 12, 18. Okay. So you can check yourself. You can see in the calculator if you're doing it right. It's not too bad. Alright, so let's look at some more examples here. Example 7 says, where possible, find each product. So for A, we have this matrix here, 4, 2, 1, 3, and this one 1, 2, 3, 4, 0, 2, negative 1, 6. This matrix is a 2 by 2. This one has 2 rows and 4 columns, so it's a 2 by 4. We look here at the inner numbers. They are the same, so we know that our answer is going to have the outer numbers of its size, so it's going to have an answer that is a 2 by 4. So I'm going to set up a 2 by 4. And then we'll get ready to multiply it. So this is the first row, first column. So I'm going to take the first row, 4, 2, multiply it by the first column, 1, 0. So I'll have 4 times 1 plus 2 times 0. This is the first row, second column. So I'm going to take the first row, 4, 2, multiply it by the second column, which is 2, 2. So 4 times 2 plus 2 times 2. The next one, this is the first row, third column. So I'm going to take the first row, 4, 2, multiply by the third column, 3, negative 1. So I'll have 4 times 3 plus 2 times negative 1. And then this is the first row, fourth column. So I'll take the first row, 4, 2, multiply by the fourth column, which is 4, 6. So I'll have 4 times 4 plus 2 times 6. Down on the bottom row, this is row 2, column 1. So I'm going to take row 2, which is 1, 3, multiply it by column 1, which is 1, 0. So I'll have 1 times 1 plus 3 times 0. This is row 2, column 2. So I'm going to take row 2, which is 1, 3, multiply it by column 2, which is 2, 2. So I'll have 1 times 2 plus 3 times 2. This one is row 2, column 3. So I'm going to take row 2, which is 1, 3, multiply it by column 3, which is 3, negative 1. So I'll have 1 times 3 plus 3 times negative 1. And then lastly, this is row 2, column 4. So I'm going to take row 2, which is 1, 3, multiply it by column 4, which is 4, 6. So I'll have 1 times 4 plus 3 times 6. And then we can clean it up. 4 times 1 is 4, 2 times 0 is 0, 4 plus 0 is 4. 4 times 2 is 8, 2 times 2 is 4, 8 plus 4 is 12. 4 times 3 is 12, 2 times negative 1 is negative 2, 12 plus negative 2 gives us 10. 4 times 4 is 16, 2 times 6 is 12, so we have 16 and 12, which makes 28. Down here, 1 times 1 is 1, 3 times 0 is 0, 1 plus 0 is 1. 1 times 2 is 2, 3 times 2 is 6, so we have 2 plus 6, that gives us 8. 1 times 3 is 3, 3 times negative 1 is negative 3, 3 plus negative 3, that gives us 0. And then 1 times 4 is 4, 3 times 6 is 18, so 4 plus 18, that gives us 22. And so there is our answer. And again, we could do this in the calculator. I'm going to go over here to, let's turn my calculator back on. Go to matrices, we're going to edit. We need to make matrix A be a 2 by 2, which has 4, 2, 1, 3 in it. And then we'll make matrix B be a 2 by 4 matrix. And it's going to have 1, 2, 3, 4, and 0, 2, negative 1, and 6 in it. And once I have those both in there, then I can do A times, wrong button, A times B. So there we go. 4, 12, 10, 28, 1, 8, 0, 22. It matches what we did. Okay. B, we have the same two matrices, but now we're doing it in a different order. So we have this one, which is a 2 by 4, and we're multiplying it by this one, which is a 2 by 2. If we look at these, are they the same? No, they're not the same. So this answer is not possible. It is not possible to multiply these two matrices together. And we can actually see that if we go to this calculator and we say, hey, let's take that second matrix B and multiply it by that first matrix A, you'll see it says dim mismatch. Dim is short for dimensions, so it's saying there is a mismatch in the dimensions, and so the multiplication is not possible. So here we have some properties of matrix multiplication. If you look, you can do an associative property. If you have matrix A times matrix B and then times matrix C, you can change the order and do matrix B times matrix C and then do times matrix A. As long as you keep them in the same order, as long as it's still ABC, ABC, it doesn't matter if you do AB first or if you do BC first. Okay. Distributive property, if you have matrix A times matrix B plus matrix C, you can distribute the matrix AN and you can get matrix AB plus matrix, it should be AC, not BC, it should be AC there. The associative property of scalar multiplication says if you have a scalar times a multiple AB, then that's the same thing as if you took the scalar times matrix A and then multiplied by matrix B. So you get the same result. Now, one thing to stress right here is that the commutative property does not work. AB is not necessarily the same thing as BA. It is possible that it could be the same thing as BA, but it is highly unlikely. Most times AB and BA are going to be two different things. Okay. The next thing we're going to talk about is the multiplicative identity matrix, which we usually call the matrix I. The multiplicative identity matrix is a matrix where when you take your matrix A and you multiply it by this identity matrix, you still just have matrix A. Or if you take the identity matrix and you multiply it by matrix A, you still have matrix A. Now, how do you make an identity matrix? It's actually really simple. You make a square matrix that has ones in the diagonal going from the upper left to the lower right and zeros everywhere else. You might recognize this because it looks really similar to our row echelon and reduced row echelon form that we talked about in 8.2. The two are actually related. They are tied together a little bit, and we'll talk more about that later. But that's what it looks like. An identity matrix is a square matrix that has ones in the diagonals and zero everywhere else. Now, because these things are identities, one thing to know is that, remember in old school multiplication, how if you took A and you multiplied it by 1 over A, you got 1. Or if you took 1 over A and you multiplied it by A, you got 1. That property in old school multiplication was called the multiplicative inverse, meaning 1 over A is the multiplicative inverse of A. It's the inverse, meaning it flips. So A times 1 over A always gives you 1. Well, there is a similar thing in matrices. There is an inverse matrix. Okay. The inverse matrix, we read it here, it's A with a little -1 superscript. That's not a power. That little -1 there just tells us it's an inverse. So this is A inverse. Now, just like here, where you took A and you multiplied it by 1 over A to get 1, here you're going to take your matrix A and you're going to multiply it by A inverse, and when you do, you'll get the identity matrix. Or you can go the other way. You can say, hey, I'm going to take my inverse, multiply it by the original A matrix, and that'll also give you the identity matrix. Okay. So what we're going to do here in example 8 is we're going to show that two matrices are inverses of each other by multiplying them together. Okay. So we're going to take A times B, and we're going to multiply these things together. Now, A is a 2 by 2, B is a 2 by 2. They have the same dimensions here, so that's okay. So our answer is going to also be a 2 by 2. Okay. So this is first row, first column. We would take this first row of A, -1, 3, multiply it by the first column of B, 5, 2. So we would have -1 times 5 plus 3 times 2. Here, this is row 1, column 2. So we're going to take row 1, negative 1, 3, multiply it by column 2, which is 3, 1. So we would have negative 1 times 3 plus 3 times 1. Down here, this is row 2, column 2. So we would take row 2, which is 2, negative 5, multiply it by column 2, which is 5, 2. So we would have 2 times 5 plus negative 5 times 2. And then in our last spot here, this is row 2, column 2. So I'm going to take row 2, which is 2, negative 5, multiply it by column 2, which is 3, 1. So we'll have 2 times 3 plus negative 5 times 1. If we clean that up, this is negative 5 plus 6. This one is negative 3 plus 3. This one is 10 plus negative 10. And this one is 6 plus negative 5. Cleaning it up all the way, we get 1, 0, 0, 1. Is that an identity matrix? Yeah, it is. It's got the 1s in the diagonals, 0 everywhere else. So that works out. That's fine. Then we need to do the other way. We need to check BA. Now, again, these are both 2 by 2s, so we can expect our answer is also going to be a 2 by 2. So this time I'm going to do, this is row 1, column 1. So I'm going to do row 1 of matrix B, multiply by column 1 of matrix A. So I'm going to have, row 1's 5, 3, and then negative 1, 2. So I'm going to have 5 times negative 1 plus 3 times 2. Over here, this is row 1, column 2. So I'm going to take row 1, which is 5, 3, multiply it by column 2, which is 3, negative 5. So 5 times 3 plus 3 times negative 5. Down here, this is row 2, column 2, or row 2, column 1. So I'm going to take row 2, which is 2, 1, multiply it by column 1, which is negative 1, 2. So I'll have 2 times negative 1 plus 1 times 2. And then lastly, this is row 2, column 2. So I'm going to take row 2, which is 2, 1, multiply it by column 2, which is 3, negative 5. So I'll have 2 times 3 plus 1 times negative 5. Clean it up. We have negative 5 plus 6. And then we have 15 plus negative 15. And then we have negative 2 plus 2. And then 6 plus negative 5. Cleaning it up all the way, we get 1, 0, 0, 1. Is that an identity matrix? It sure is. So since both of these products came out as an identity matrix, we can say that A and B are inverses. Or if you wanted to, you could say that B is equal to the inverse of A, or A is equal to the inverse of B. Whichever way you want to think about it. Okay. And again, we could have done these checks with a calculator. We could have programmed both of these in as matrices, multiplied them together, and gotten our answer and seen that they are both the identity matrix. Alright. So how do we find an inverse? Well, there is a long way and a short way of doing it. The long way involves taking a matrix and turning it into an augmented matrix, where on one side you have your original matrix A, and on the other side you have your identity matrix I sub n. Okay. Then what you would do is you would perform operations to change your matrix A until it turns into matrix I sub n, the identity matrix. And as you do those changes to matrix A, that also changes the right side. And instead of being an identity matrix on the right, it becomes a different matrix B. That matrix B that ends up over there, that is your inverse matrix. Now, that's the long way. The short way is program your matrix into your calculator and tell the calculator to do the inverse. And so that's what we're going to do right here. So I have a matrix and I want to find the inverse of it. So I'm going to go in here, I'm going to edit my matrix, and this is a 3 by 3, so I'm going to put 3 by 3. And I'm going to put these elements in there. 1, negative 1, 1, 0, negative 2, 1, negative 2, negative 3, and 0. Okay, and double check that I put them in right. Yep, that all looks good. Okay, so I'll quit out. I'll go back to my matrix menu. I'm going to pick matrix A. And then after I pick it, I'm going to hit this little button that has an X to the negative 1 on it. And see, that puts a little negative 1 up above it. So now this is saying take A and do the inverse. And so when I hit enter, there is my inverse matrix. Oops, and I already wrote that A, so I just need to copy down my matrix. So let's see, 3, negative 3, 1. Negative 2, 2, negative 1. Negative 4, 5, negative 2. Negative 2. Okay, so there is my inverse matrix. Okay. Now you can test that you did it correctly because we can take this one and type it into our matrix B. So matrix B, make it be a 3 by 3, and just type in this answer that we got. 3, negative 3, 1, negative 2, 2, negative 1, negative 4, 5, negative 2. And so I put that in matrix B. Well, now if I go into my matrix menu and I multiply matrix A and matrix B, because they're inverses, I should get an identity matrix, which I do. And I can also go the other way. I can say, hey, take matrix B and multiply it by matrix A. And hey, look, it gives me an identity matrix as well. So you can actually test it and see if it works or not. Okay. Now, why do we care about inverses? Well, we can actually use inverses to solve a system of equations. So let's say we had a system of equations where we had a1x plus b1y plus c1z equals d1, a2x plus b2y plus c2z equals d2, a3x plus b3y plus c3z equals d3. Well, this system can actually be turned into a matrix equation, where here you have a matrix that's a 3 by 3 made up of your coefficients, a1, b1, c1, a2, b2, c2, a3, b3, c3. Over here you have a matrix that is just your variables, x, y, and z. And then equals, over here you have just your constants, your d1, d2, d3. Now we usually call this matrix that has the coefficients A, which you can see right here. We usually call this matrix that has your variables in it X. And then we usually call this matrix that has your constants in it B. So what we have is an equation, AX equals B. Well, how would you solve this for X? Because that's what we want to do when we solve a system, right? We want to know what X, Y, and Z are. So we want to know what this matrix is. Well, to get rid of a matrix, to get rid of a multiplication of a matrix, you have to do division. Well, division is really the same thing as multiplying by the inverse. So what I'm going to do is I'm going to multiply both sides by A inverse. Now, when I do A inverse times A, remember that these inverses cancel each other out and they just leave an identity matrix. So I have I times X equals. Over here, I'm just going to have A inverse times B. Now, remember from your notes just a minute ago, when you multiply an identity matrix times x, or times any matrix, you just get that same matrix. The identity matrix doesn't change it. So we're going to end up with x equals A inverse times b. So this matrix that has our answers, x, y, z, we can find it by multiplying the inverse of our coefficient matrix times our b, which is the constant matrix. So this is actually a really nice way to solve a system of equations. And you can kind of see I showed the work over here as well. So to solve a system of equations, all we have to do is take A inverse and multiply it by B. And so that's what we're going to do here in this last example. So it asks us to solve the system by using A inverse, the inverse of the coefficient matrix. So I'm going to start by defining my matrices. So matrix A is the coefficients. So here in front of x, I have 1. I don't have any y's, so it's 0. And z's, I have 2. For my second equation, I have -1 for x, 2 for y, and 3 for z. And in my last equation, I have 1 for x, -1 for y, and 0 for z. My B matrix is the matrix of the constants, which in this case is 6, -5, 6. So now what I'm going to do is I want to find A inverse. Okay, so I'm going to go to my calculator. I'm going to program this A matrix in and this B matrix in really quick. So I'm going to go over to edit. For my A matrix, it's a 3 by 3, so I'm going to leave that alone. But I'm just going to put in these numbers: 1, 0, 2, -1, 2, 3, 1, -1, and 0. I'll quit. I'm going to go back over to edit. I'm going to edit the B matrix. Now this is a 3 by 1, 3 rows in 1 column. And it has 6, -5, and 6 in it. Oops. And then I will quit. So I want to find A inverse, so I'll go to my matrix menu. I'll pick matrix A, and then do the inverse. So there is A inverse. So A inverse is 3, -2, -4, 3, -2, -5, and -1, 1, 2. Okay. So to find my answers, I take A inverse and I multiply it by B. Now we could do this multiplication by hand, but I'm just going to let the calculator do it for me. So I'm going to go to my matrix menu. I'm going to pick A, then I'll pick inverse, then I'll go back to my matrix menu and I'll pick B. So it says A inverse B. I'll hit enter, and it gives me my X matrix, which is 4, -2, and 1. Now remember, this is our X matrix, which is our matrix of our solution, X, Y, Z. So my solution should be 4, -2, 1. And we can check that. We can actually take these and plug them into the equation and see if it works. So 4 plus 2 times 1, that's 6. That matches that one, that's fine. For the second equation, -4 plus 2 times -2 plus 3 times 1, that gives us -5, which that matches. And then for the last one, 4 minus a -2, that gives us 6. That matches that. So we can feel pretty confident that is the solution to this system of equations. So this method, using A inverse, is just another way that we can solve a system of equations. It's a slightly different way using matrices. It's different than the other way we use matrices to solve the system in 8.2. but it is an equally valid method. It is a method that you could use to solve a system of equations. Okay. So that is it for 8.4. As always, if you have any questions, feel free to send me an email.